So far we have looked at the definitions of random variables and probabilistic distributions. We'll now look at the central paradigm of probabilistic reasoning, and which is to identify all relevant random variables x1 to xn of the environment and make a probabilistic model which we denote as the joint distribution or the probability distribution of all the random variables that models the interactions. And once we have the model or the probabilistic distributions of all the random variables, we'll then look at how to do probabilistic inference or probabilistic reasoning by introducing evidence that sets some of the random variables in a known state and subsequently computing the probabilities of interest conditioned upon this evidence. We'll call these conditional probabilities, which we will define later. And so to this end, we require the definitions of joint probability, marginalization, conditional probability, Bayes rule, and independence, which we will now look at the definition in closer detail. But we will look at a small number of variables, random variables in our definitions in this lecture. And in the subsequent lecture, we'll look at the use of the uh, these definitions together with graphical model for a large number of random variables. We'll see that the naive definition or the naive way of doing things, it would make a lot of probabilistic modeling and inference intractable together with the definition of graphical models, and we will see that we'll be able to make the probabilistic modeling and inference in a much more tractable way. So the definition of joint probability, suppose that we consider a combination of events of two random variables. For example, x is the flipping of a coin, which can either take a head or a tail, and as well as y would be the flipping of another coin, which would also take head or tail. So now the joint event of this x and y would be to flip the two coins together at the same time, and we can see all the outcome space of these two events would be either head head, head tail, tail head, or tail and tail, and we can assign a certain probability to this joint distribution, which we denote as p x comma y over here, and in this case is a discrete probability distribution where each one of these will take a certain number and it better sums out to equals to 1. The summation has to be equals to 1 to make it a valid probability distribution. And of course, x and y can also be a continuous space where it's simply represented by a function of x and y in this case over here. It could also be a discrete continuous where one of the variable, for example, y is over here, it's a discrete number, and x can be a continuous random variable. And this is, so as I have mentioned earlier, that this is captured in the joint probability distribution, which we denote as p x comma y, or it's simply read as the probability of x and y. Of course, it can be more than two random variables, as we will see in the subsequent lectures where if this number of random variables is very high, we'll see that the inference as well as the learning of this model would become intractable if we do it naively, and we need graphical modeling to make it into a tractable process. So the of after we have defined the joint probability, the next thing that we need to define would be the marginalization of the probability. So we can marginalize a joint distribution to obtain the joint probability by summing up over all other random variables. So this is because of the summing up or integral process. This is also otherwise known as the sum rule of probabilities. So for example, if we are given a joint probability of p and y, we want to find the marginal probability of x. And here, since we do not want y in the final marginal probability, we will marginalize it out by integrating over y. In this case, x and y are both continuous random variables, so we will do an integration. Similarly, if we want to find a marginal probability of y, we would want to marginalize out x, which we otherwise call the Nielsen variable, and by doing integration over x, since x and y are both continuous random variable. Of course, this marginalization can also be done on a discrete random variable of given a joint probability where x and y are both discrete random variable. If we want to find the marginal probability of x, this means that we want to remove the uh, Nielsen random variable of y. Will simply sum up all the possible values of y over here. So what this means is that suppose that I'm given a joint probability of x and y, where x and y takes a certain state. So for example, y takes a state of 1, 2, 3, 4, 5, 6, 7. These are all the possible outcomes of y, and of the random variable y, and x similarly takes 1, 2, 3, 4, 5, 6, and 7 states. So each one of these, there will be a entry of a certain probability number. So the joint probability of x and y means that all these numbers that are given as probability, it should sum to 1. It should sum to 1. Everything here, all the numbers here, the total probability for the joint probability of x and y, it should sum to 1. And what we, when we talk about the marginal probability of x, this means that we want to marginalize out y, and we have to sum out over all the possible values of y. So here, in this case, it will become probability of x over here, the marginal probability that we want to find. So the operations that we need to do here would be simply to look at the table of the entries in the joint probability, and for every value of so for every value of x, for every state of x, say for example 1 over here, x equals to 1 over here, what I want to do here is that I want to marginalize over y. That means that I want to sum up over all the possible values of y. This means that I want to sum this number, this number, this number, and so on and so forth in this whole column over here, and put it into this entry here. So we'll do the same process for every state of x over here. So when x equals to 2, I will sum up all the numbers over here and put it inside here. And similarly, for all the states, the remaining states of the x, I'll sum out the whole column and then put it into the entry where x equals to 7 in this particular case over here. So we'll do the same thing for the marginal probability of y. So what this means is that I'm going to sum up for every state of y, I'm going to sum up all the values in the joint probability table for x. So in this case, let's say I want to look at the case where y equals to 1. I would simply sum up all the values of x that corresponds to the state of y equals to 1 and put it into this particular table here. So similarly, for example, y equals to 3, I'm going to look at this row and sum up every value and put it into y equals to 3 here. Of course, the marginalization rule also works for a joint probability distribution of discrete continuous random variable. Now suppose that we have a joint probability distribution p, x, and y, where x is a continuous random variable and y is a discrete random variable. To find the marginal probability of x, we will simply need to sum up over all the values of y. And similarly, to find the uh, marginal probability of y, which is a discrete random variable, we need to integrate over the all the values of x, since x is a continuous random variable. The marginalization rule also work for higher dimension, and here suppose that we are given a joint probability distribution of w, x, y, and z for random variables, where w is a discrete random variable and z is a continuous random variable. To find the joint probability of x, y, we simply need to integrate over z, which is a continuous random variable, and sum up over the discrete random variable of w. So another example here would be if we want to further find the marginal probability of x, for example, then this would be equivalent to taking the integral over dy, and suppose that where we suppose that y over here it's a continuous random variable. Now, the next thing that we look at would be the conditional probability, uh, which we write as the probability of x conditioned upon y equals to a certain value, a fixed value, which we denote as z star. This otherwise read as the probability of x given y equals to y star. So here we can treat y equals to y star as the evidence that we were talking about earlier, and because we already observed that the random variable is taking a certain state of y star, and this would be the evidence. And to find the probability of x, where x is a random unknown or a latent random variable that we want to figure out what's the possibility or what is the probability of it happening when we saw that y is taking a certain value, or otherwise we can also call y this as our observation over here, and x is our unknown random variable, or otherwise known as the latent random variable. And we'll see that this conditional probability is also known as the chain rule or the product rule of probability, and it gives us the relative propensity of the random variable x to take a different outcome, given that we have observed y to be fixed at a certain value of y star. So intuitively, what it means is this: that suppose that we have a joint probability of p of x and y, which is given by this distribution over here, and if we observe that y takes a value of y1, then what we are looking at over here of the conditional probability of x condition upon y equals to y1 would be this particular slice of the joint probability distribution normalized by the total sum of the of the distribution probability distribution at this slice. This is because we want to make it a valid distribution where the area under this curve must be equals to 1. So the division is actually a normalization function. So similarly, if we look at the case of where y equals to y2, that means that we observe that the random variable of y takes a state of y2, then what we are looking at, the conditional probability of x condition upon y equals to y2 is this particular slice that corresponds to the uh, the state of y equals to y2 divided by the total probability under this slice. So this is just to normalize the conditional probability to make it a valid distribution such that it sums out to 1. And uh, the so here more formally, the conditional probability of p x condition upon y equals to any state of y star, a generic state of y star, is equals to the joint probability of y equals to y star. This means that we are looking at this particular slice where y takes a certain value, for example y equals to y1, divided by the uh, total sum of the probability under this particular slice. So here this can be written as the integration of dx, because I'm integrating, I'm summing out over all the possible values of x under this slice of y equals to y star. And this is equivalent to, this part here is equivalent to the marginal probability, of y equals to taking a value of y star. And the conditional probability is usually written in a more compact form. Instead of writing y equals to y star over here, we'll simply write it as px condition upon y. So here, y, when I write condition upon y, it simply means that y here is observed to be fixed at a certain value. And this would be equal to the joint probability of x and y divided by the marginal probability. So this is actually a normalizer, the normalizer that makes this whole thing a valid probability. This means that the sum of this must be the total sum of this. If we take an integral over dx, it must be equals to 1. So this normalizer plays a very important part to make it a valid probability, which we can now rearrange the conditional probability into this particular form by moving the denominator, the normalizer up onto the left hand side of the equation. That gives us the two different forms over here. The joint probability of x and y equals to the conditional probability of x conditional given y multiplied by the marginal probability of y, and as well as equals to the conditional probability of y given x multiplied by the marginal probability of y of x. So this multiplication here gives the name of product rule, which is also used to describe conditional probability. And of course, this works for higher dimensions too. So suppose that we are given the joint probability of 4 random variables, w, x, y, and z. We can see that we can write this product rule as into this particular form over here. We can verify that this is correct by looking at this, by moving this guy here to the left side, where we say that x, w, y, and z divided by p of x. So when we divide by this particular normalizer, the marginal probability, we'll simply add the condition upon this guy over here. So this becomes w, x, y condition upon z, which is this guy over here. So we can similarly, what we can do here would be to given this three random variable condition upon z, we can further break this down by using the product rule to get these two terms over here, and then we can also break this term over here into these two terms over here. And finally, this higher dimension joint probability can be written as this form over here using the product rule, or otherwise known as the chain rule. Now, the product rule gives rise to what we call the Bayes rule. And recall that there are two different ways of writing the joint probability using the product rule, as written over here. So in this case, we can see that in both of these equations, it contains the joint probability distribution of x and y. And if we were to eliminate the joint probability in these two equations and combining them into one equation, this is what we will get. We will get this guy here to be equals to this guy over here, and then rearranging this by making the conditional probability of y condition upon x as the subject, we will get this form over here. And we can see that the denominator, which is the marginal probability of x, can be also written into this form, the marginalization form, where we marginalize out y in the joint probability of x and y. And this can be also, this guy over here, the joint probability, can then be rewritten into the same form as the numerator, and we'll get this form over here, which is equals to the conditional probability of y upon x. And this thing over here would be known as the Bayes rule. So here's some formal terminology that we use in the Bayes rule, uh, where we always call the left side of the equation. Suppose that we have a conditional probability over here of y condition upon x. So y here must be this particular equation here must be the posterior distribution, where y is the latent variable or the unknown random variable condition upon x after observing x. So this x here must be the observed random variable. And it's always the case when we write the Bayes rule that this this term on the left side, it must be the posterior, where the first random variable here must be a latent, and the second one, condition upon it, would be an observed random variable. And on the right side over here, we are going to flip this around, where we say that it's a conditional probability of x condition upon y. And in this case here, we call this the likelihood, where this likelihood is the probability distribution of observed random variable condition upon the latent random variable. So this simply means the propensity for observing a certain value, given that we know that y has already, the latent random variable has already taken a certain value. And this is important because in the real cases, this is what we always observe, the likelihood, and it can be given by, for example, the robotic sensors, a laser sensor, a wheel odometry, for example. So this will always be returned from the sensors. And then we will have some priors. We will have some prior knowledge uh, of the latent or unknown random variable before even we see x. So this term is important, and it's the key differentiator between the Bayesian approach and the frequentist approach, where in the frequentist approach we only care about the likelihood, and in the Bayes approach there is a certain prior. That means that we take prior knowledge that we have about the unknown random variable that we wish to estimate, and into the posterior probability distribution. And there is a normalizer here, which is also called the evidence. This is a constant, where because we marginalize out all the possible states of the latent random variable and leaving the observed random variable over here. So after integrating out uh, all the latent random variable, this guy here becomes a constant. And this acts as a normalizer to make the posterior distribution a valid probability. This means that the integration or over all possible values of y needs to be equals to 1 in this case. So now let's look at a simple example to illustrate the use of these uh, rules that we have seen earlier. Let the random variables b and f represent the box color. So we are given two boxes, and we'll use b to represent the box color. It could be either a red box or a blue box. And the type of fruits is denoted by the random variable f that is contained in the respective box, where the value of b, as mentioned, that it could be a red box or a blue box, and the values of the random variable f, which is the fruit type, it could be apple, which we denote as small a over here, and the orange, which we denote as small o over here. So now we are also given the probabilities of selecting the red or the blue boxes as 0.4 and 0.6. Now this is a biased probability. This means that the person choosing, most of the people who are choosing these boxes, any one of these box, their tendency is that, or their preference is skewed towards the blue box. They have a higher probability of selecting the blue box. And next, we are also given the conditional probabilities for the type of fruits given the selected box. Now, suppose that the box is, we have already selected the box to be a red box, means that we are conditioning this probability that B equals to the red box. Of the probability of choosing an apple would be 0.25, and the probability of choosing an orange would be 0.75. Notice that these two probabilities here condition upon the case where the box it's equals to a red color. The total probability of selecting the fruit would be must be equals to 1, and this means that we are ignoring the fact that we have already selected the box. Similarly, when the box is when the box that is selected is a blue box, we will see that the probability of selecting a apple would be 0.5, and the probability of selecting an orange would be 0.25, and these two must sum out to be 1 as well. Now, we'll find the overall probability of choosing an apple. This means that we want to find the marginal probability of the fruit being an apple. And what we want to do here would be to simplify the probability of F over here. And then the next question is that we want to identify the color of the box if we observe that an orange has been selected. So we already observed that an orange has been selected. So this would be the conditional probability of the selecting the color of the box conditioned upon that the fact that the fruit that we have select is equals to an orange. So this is the probability, the conditional probability that we want to find. Now first, let's look at the marginal probability of the fruit to be chosen to be an apple. We can see that this is a marginal probability. So what we want to find here would be the probability of F, and this can be written as the marginalization, because we can see that there's no box color in this marginal probability. Hence, we need to marginalize out the color of the box from the joint probability of F and B. And we can see that the joint probability B, as we have defined earlier on in the product rule, that this guy over here is given by the probability of F conditioned upon B multiplied by the probability of B, which is what is written here. Now let's look at the case where the fruit that is selected is an apple, where we denote as the probability of F equals to A. We'll simply plug this guy over here. We'll simply make the fruit type to be equals to A in an apple in the marginal probability given by this guy over here. And we can see that since we are summing up over B, where B here takes it can be blue or red. So we are going to sum up this over all the possibilities of the of the box, which can be either blue or red. We can see that we simply write this as since F is already equals to A, we will write this down over here. So the first term here in the summation would consist of the case where the box equals to red color. And then the second term here, so this is the first term that we've seen here. And the second term would consist of the case where the box equals to blue color. So all these probabilities can already be found here, which is the probability that the conditional probabilities that we are given earlier on. And we can simply plug in the values and into this the individual conditional probabilities and marginal probabilities, and we can simply find out that the probability that the fruit that is chosen equals to an apple is 0.55. Next, we will move on to look at the conditional probability of identifying the color of the box if we observe that an orange has been selected. So this, as I mentioned earlier on, it's the we are finding the conditional probability of the color of the box uh, conditioned upon that the fruit that has been selected is equals to an orange. So we'll make use of the Bayes rule to find this. We can write this first. We'll consider the case where the box that is selected equals to is a red box, and condition upon the case where we an orange has already been selected. So using the Bayes rule, with this is the posterior that we are interested in. We'll have to flip this around where we write this as a likelihood. So notice that this follows the definition, the terminology that we have defined earlier for the Bayes theorem, where B here, the color of the box, is the latent variable, is the unknown latent variable, and F here is what we have selected, what we have already observed. So this is the observed random variable, and hence this guy over here on the left side is called the posterior. And in the first term in the right side of the equation of the Bayes theorem is where we flip these two random variables around, and since F here is the observed random variable and B is the latent uh, random variable, this guy over here is known as the likelihood. We'll multiply this by a prior term where we have some prior knowledge about how likely we are going to choose the box to be a red color, for example. So this is the latent. We have some uh, prior knowledge about the latent random variable conditioned upon the evidence or the normalizer over here where f equals to 0. So since this guy here is independent of the latent random variable, it's only a function of the observed random variable, we will say that this is a constant over here, or this is actually a normalizer that makes the probability, the final posterior probability, a valid one. So here, looking at all these terms over here, we can see that these are all the values that are given here, the respective values that are given here. We can plug them in and compute the conditional probability. So now, once we have this conditional probability, the next thing that we need to find would be the conditional probability of the box equals to that is selected. If it's a blue box, condition upon the fruit that is selected is an orange. So we can, since these two probabilities over here, since B is a binary state, there are only two uh, possibilities for the box. We will know that we know that the sum of these two probabilities, sum of these two conditional probability, conditional upon the same uh, f equals to orange, the fruit type equals to orange, where all possibilities of overall possibilities of the box color, it must sum up to 1. So this simply we do not need to use the Bayes rule to evaluate this anymore. It will be simply 1 minus this probability that we have found earlier on. And here the results shows us that the orange is more likely to be selected from the red box. The next thing that we need to define is the independence of probability. So when we say that the independence of two random variables x and y, it means that every conditional distribution is the same, and the value of y, observing any y to take any value, it actually tells us nothing about x and vice versa. So recall that the conditional probability, it's actually a normalized slice of the joint probability distribution that we have seen in the earlier slides. And what's interesting here is that when the two random variables are independent, what it means is that the slice that we take, any slice that we take across here, suppose that I take a slice of y equals to y1 after normalization, and another slice of y equals to y2 after normalization, the distribution, the conditional distribution of x conditional upon any y would be the same. And this means that by observing y to take any certain value, I'm unable to tell anything about x because it's all the same. It's all the same over here. So this can be rewritten as y x conditional upon y, where y is observed is simply equals to p of x because I don't get any information of x by observing y. And similarly, y conditional upon x. This means that if I take a slice here and normalize it, another slice and normalize it here, uh, the probability of y would still be the same for condition upon any x over here. So I can rewrite this as the probability of y. And what this also means is that x and y are probably disjoint in the event space. And here it also applies to the discrete probability distribution of x and y. What it simply means is that if I have a joint distribution where x and y are discrete random variables, after taking a slice of the joint probability where y equals to y1 over here and normalizing it, there won't be any difference of the final probability table compared to taking y equals to y2 and normalizing it over here. So this gives rise to an interesting observation where when the variables are independent, the joint probability actually factorize into simply the product of the individual marginal probability. And the last definition that we will look at is the expectation, which will give us the average value of some function taking into account the distribution of the random variable x. And the definition is that is given by these equations over here, where we say that the expected value of the function fx is equals to the marginalization of the function multiplied by the probability distribution of the random variable x. And similarly, it works for both cases where x is a continuous and a discrete random variable, with the difference that if x is a continuous random variable, we put the integral sign, and if x is the discrete random variable, we put a summation sign over the marginalization. Now, the first rule here is that the expected value of a constant is the constant itself. So this can be easily seen where if the function is a constant, which is denoted by kappa over here, uh, we will see that the expected value of this function kappa is actually equals to the integration over x multiplied by kappa multiplied by kappa multiplied by the probability distribution of dx. Since this guy is a constant, we can pull it out, and the remaining would be an integration of px over dx, and this is equals to 1, since px must be a valid probability distribution. And the second rule is that the expected value of a constant times function is constant times expected value of the function. What it simply means here is that if I want to find the expected value of the constant, which I denote as kappa over here, and multiply by a function itself, it would be equivalent to the constant multiplied by the expectation of the function itself. So this can also be easily seen where this guy over here multiplied by the function f is equals to the uh, integration of over x of the constant multiplied by the function multiplied by the probability of x integrate over x. So we know that the integration doesn't affect the constant, so we can pull this constant out and rewrite this into this particular form over here, where this guy over here is simply the expected value of fx itself. And the third rule that we have we will look at is the expectation of the sum of the function is the sum of the expectation of the function itself. So here, what it means in equation is that if I were to take the expectation of two functions, f and g over here, this follows the principle of linearity, where I can actually take the expectation of f plus the expectation of g itself. So this is also simple, where so since this guy here is equivalent to the integral of f plus g multiplied by p of x dx. So we can rewrite, since integration follows the principle of linearity, we can rewrite this into integration of f multiplied by px dx plus the integration of g multiplied by px and dx itself. So this would be equivalent to the sum of the expectation of the respective function. And the final rule that we'll look at is that the expectation of the products of function in variable x and y is the product of expectation of function if x and y are independent. So this means that if I were to multiply these two together and take the expectation, if x and y are independent, then it would be the multiplication of the expectation of the two. So this is easily seen from here, where this guy here is equals to f multiplied by g multiplied by p of x multiplied by p of y and dx and dy. So yeah, because I'm writing this as a independent product which forms the joint probability of x and y, because x and y are independent. So hence I can rewrite this into this particular way over here, and this simply becomes the integration of f multiplied by p, then multiplied by uh, g multiplied by py and dx dy, which can be rewritten into two separate forms of since this is independent, the first product is independent of y, I can rewrite this into fpx dx multiplied by the integral of g multiplied by py dy, which is equivalent to the multiplication of the two expectations of the respective functions.